All right, so let's look at these. Again, I'm going to kind of shortcut them a bit and help you see what the reactions are. So we know that I could replace this distributed load to find the reactions with an equivalent load. That would be the area under the curve, which would be L times W naught. So that's the equivalent. And acting through the centroid, this would be L over 2, right? So I think if you took enough time, you would see that the reaction force here is W naught L, and it's up. So what kind of shear is that? Shear force. Up on the left side. Positive. And then you can see that the moment is in this direction, and it's W naught L squared over 2. And what kind of moment is that? Bending moment. Positive or negative? Negative. So I know where I'm going to start, shear, and moment. That's why it's important to get the reactions to start the problem. Oh, by the way, over here, what kind of bending moment should I end up with? Zero. So let's do the shear problem. So I'm going to start with a shear of W naught L. And I'm going to apply my reactions. I know that the change in shear is the area under the load curve. So I look up here, I see a continuous load. What's the area of this load curve? Well, I've actually already calculated it. It's W naught L. Is that a positive or negative load? Negative. So if I start at W naught L and I subtract W naught over L, what should I get? Zero. What's the shape of the curve? Well, according to my theory, the slope of the shear diagram is equal to the load. So if I start here, what's the value of the load? Minus W. What's it here? Minus W. What's it here? In fact, it's minus W everywhere. What kind of curve has a constant slope? A straight line. And the slope of that line is minus W naught. So there's the shear diagram. Where's my shear max? At the fixed connection, and what's its value? W naught L. And it decreases linearly to 0. So now I can use this and similar relationships to construct the moment diagram. So starting here at the left side, what's my bending moment? We computed it. It's negative W naught L squared over 2. And what do we think the moment here at the free end is? 0. So, again, I know where I'm starting. I know where I'm going to end. So let's check that first. Well, we know that the change in moment is what? The area under the shear diagram. What is the area under the shear diagram? Well, it's a triangle, right? So it's going to be 1/2 base times height. So WL times L divided by 2, that's positive WL squared over 2. If you add that to negative WL squared over 2, you get 0. So that's good. What's the shape of my moment diagram? It's equal to the shear, right? So let's start here. What is the value of the shear right here? It's positive W naught over L. So I'm just going to sketch that in. There's a positive slope. You see that? And the slope does what as I move to the right? It gets smaller and smaller and smaller. In fact, at this end, it turns into, what kind of slope is 0? A horizontal line. So I know that my curve has to have a slope 0 and a positive slope here. So all I do is sketch in a parabolic curve that fits those two. Now this curve is not precise in its ordinate values, but it's got the right shape and it's got the right limiting values. So now you know the variation is quadratic, but more importantly, you can tell me what's the maximum moment in the beam. Well, it's WL squared over 2. Is it positive or negative? Negative. Is it becoming clearer? All right. So this next one will test our geometric abilities. Let's go to this guy, and like we did before, let's find the concentrated equivalent of that. So the area under a triangular load is 1/2 base times height. So that will be W naught L over 2. And the distance from this end will be 2L over 3. So again, if you look at the reactions, if you sum forces in the y direction, you'd find the reaction force was up and equal to W naught L over 2. This force balances that force. And you would find that the moment is in this direction, and it balances this force times this moment arm, which is W naught L squared over 3. So again, I know my starting shear moments, and I know my ending shear moments. Yeah?
Why are we assuming that's negative moment?
I'm not assuming.
Or you just know it?
Well, do you see that this moment is equal and opposite of this moment?
Okay.
So equilibrium says it has to be in that direction.
Gotcha. Thank you.
But we're drawing a bending moment diagram. So what kind of bending moment is that? Negative. So let's start again. Starting the shear diagram, going left to right. What's the shear at the left side? Looks like it's W naught L over 2. Is that positive or negative? Positive. And the change in shear over the length of the load is the area under the load diagram. What's the area of this triangle? 1/2 base times height. It's W naught L over 2. What kind of load is this? Positive or negative? Negative. So I start at W naught L over 2 and I subtract W naught L over 2. What do I get? 0. And I got no shear out here at the end. There's no applied force. And what's the shape of my curve? What's given by the load? What is the value of the load right here? 0. So that means I'm going to start with a 0 slope. And then the slope slowly increases, right, to a max value of W. Is that a positive or a negative slope?
Positive.
Down is negative. So this slope over here, if you actually looked at it, would be minus W naught to 1. And all I have to do is draw up, this is linear, so this is going to be parabolic or quadratic. I just need to draw a curve that kind of fits into that. And there's the variation of my shear force. Again, as a structural engineer, what do I care about? What's the maximum shear and where does it occur? So the question is, what is the maximum shear? W naught L over 2. Where does it occur? At the fixed connection. So now I draw my moment diagram. What's the starting bending moment? W naught L squared over 2. Is that positive or negative? It's negative. So I'm going to start off at a negative W naught L squared over 3. What's the moment at the free end? 0. I can check to make sure that's true because I know the change in moments equal to the area of the load curve. I mean the shear curve. What's the area of a parabolic section? Anybody know that off the top of your head? I happen to know. It's 2/3 base times height. In case you don't know that, and you wanted to, if you look in the back of your book, they have areas and centroids of various shapes. Here's a parabolic section, and it's hard to see, but you can see the area is 2/3 base times height. And if you were to make this a rectangle, the little piece there on the side is called a spandrel, and that's it right here. And it's 1/3 base times height. And this is for a parabolic. If you go up to cubic, quartic, quintic, and keep going, any n-order curve, you can find the area of any n-order section through this. I don't expect you to memorize any of these, but you have your book, you have, what's that thing called? The internet. You can find it very quickly. I imagine if you Googled the area of an nth order degree parabolic curve, you would get this formula without any trouble. So even if you don't have a book, you should be successful. Will I expect you to do that on the exam? No. Yes?
So in the moment diagram on the left-hand figure, is that a spandrel?
This?
Yeah.
It is. But we don't care about the area under a moment diagram yet. I'm seeing the future again. Okay, so what's 2/3 base times height? Well, 2/3 base L times height WL over 2 is positive W naught L squared over 3. So if I start at negative W naught L squared over 3 and add positive W naught L squared over 3, I get 0. So this is true. What's the shape of the curve connecting these two? What's the value of the shear? What's the value of the shear right here? It's positive. So I'll just go and sketch some kind of positive slope in. Positive. And then what does it do? It decreases parabolically to 0. So I'll come over here and I'll put in a 0 slope. And all you have to do is draw a curve that connects those two. And there's your distribution of moment. Again, all we care about is what? Maximum value. Where's the maximum moment? Right there. And what's its value? W naught L squared over 3. And it's negative. Yes?
Why do you take it over 3?
I didn't take it over 3. That's the value I found. So that was this force times this distance. So W naught L over 2 is the force times the distance 2L over 3 gives me a moment of W naught L squared over 3.
So you just simplified it. Wouldn't it be...
Yeah.
Well, it'd be 2 W naught L squared over 6.
Right, yeah, that's what I'm...
Okay.